Hey everyone, my name is Rahul Ajmeria. I'm a CGOE student of CS230 and I have done this final project with Hannah and Matthew, which is basically trying to predict depression using the mobile health, basically data from smartphone sensors and trying to use a model to predict depression. For this, I have done a study on the student life dataset. Depression affects almost 280 million people worldwide. While traditional assessments have problems like infrequent surveys, self-reported subjective assessment, and limited temporal resolution, our solution here tries to stand out by doing digital phenotyping. By using data gathered from continuous behavioral monitoring via smartphone sensor, we try to predict depression. To begin with the study, we used the student life dataset, which is basically a dataset on 49 students monitored over 10 weeks with multiple smartphone sensors. Our goal is given that 7 days of behavioral patterns predict whether someone meets the clinical threshold for depression on the PHQ-9 scale, in which label with a value greater than 10 leads to depression classification. One thing to note is that our data quality assessment revealed that while our pipeline tried to target 20 features from the five sensor modalities which are listed on this slide, only the audio sensor provided sufficient coverage and reliability across participants. This resulted in a final feature set of three audio derived metrics. Our pipeline extracts daily features from raw sensor data, creates 7-day sequences, and applies a synthetic minority oversampling technique. This is to handle the class imbalance. The technique works by creating new synthetic data points for the minority class instead of simply duplicating the existing ones. This helps prevent overfitting and tries to improve the model performance. We applied a chronological splitting of 17, 15, and 70, 15, and 15 for train, validation, and test sets to prevent the temporal leakage. We also applied weighted binary cross entropy loss to provide more weightage to the minority class in the loss function. This combination was essential to improve the F1 score by 97% and recall by 139%. We systematically compared three model architectures: LSTM for sequential processing with gradient clipping, convolutional neural network with 3-day kernels for local patterns, and a transformer model with multi-headed attention for global dependencies. For training stability and optimal performance, we applied rigorous hyperparameter tuning across all models. We used clipping specifically for the LSTM to prevent exploding gradients, which was a common issue noticed. We implemented callbacks for early stopping by monitoring validation loss with a patience of 10 epochs to prevent overfitting. We also added a reduced learning rate on plateau strategy, which dynamically reduces the learning rate by 50% when validation performance plateaus, thus ensuring an optimal convergence. Each model was trained with an Adam optimizer at a learning rate of 0.01. Dropout rates between zero point 0.2 and zero point 0.3 were used for regularization, and a mode to balance the class distribution from 25% to 50%. This systematic approach ensured fair comparison across architectures and maximized each model's potential. Coming to our results, our transformer achieved 0.925 area under the curve, the convolutional neural network achieved 0.919 area under the curve, and the LSTM fell short at a 0.81 area under the curve. This 14% gap between the transformer and LSTM demonstrate that the attention mechanisms can relate any day to any other day, outperforming purely sequential processing for mental health prediction. Gaining some insights on this, we think that transformers won because LSTM processes sequentially and struggles with distinct behavioral patterns, while the convolutional neural network is limited to the 3-day kernel size, though it is fast to train. Transformers through attention succeeds in capturing non-local temporal patterns, which is a characteristic of the depression data. Even though in LSTM we use bidirectional processing and gradient clipping, it struggled with long-range dependencies. In case of convolutional neural networks, 1D convolutions extracted local patterns efficiently. Finally, the transformers architecture chose multi-headed attention, captured non-local patterns as positional encoding, and preserve temporal order, along with its layer normalization that ensures stability. To summarize, our transformer achieved the best score, demonstrating that attention mechanisms are superior for mental health prediction. Thank you for your time.